feel I have the power. Okay, so today I want to talk about a configuration, a mechanism that may model the early growth of supermassive black holes. So the context will be cosmological, and but the actual mechanism actually borrows a lot from stellar structure. So I hope I can keep your attention even during the physical mechanism itself. So, so you don't see it well, but this is the Lockman hole observed by Chandra. And most of these X-ray sources are in fact black holes if we believe that quasars and AGN are powered by accretion onto black holes. And among these sources are objects like these three sources, which are very bright quasars, a redshift 6 or so. And they have a luminosity of 10 to the 47 ergs per second. And if you assume that they emit at the maximum theoretical limit, which is the Eddington limit, you can estimate a mass of in excess of 10 to the 9 solar masses. And that's why we call these objects supermassive black holes. This means that those objects have been accreting, assembling this mass when the universe was less than 1 gigayear old, and in fact the bulk of the galaxy formation had yet to take place. So this introduces a link between black hole accretion, black hole formation and accretion and galaxy formation. So generally, one has to put forward the theory for the formation and evolution of black holes, so to account for the local demography of black holes and the quasar luminosity function at high redshift, or the presence of those objects. And I'm going to concentrate on this last point to give you a feeling of the problem or the issue. If we start with CITS, black holes, early enough, like a redshift much greater than 10, and these CITS have 10, 100 solar masses, and we let them accrete continuously at the Eddington limit, then we have just enough time to build up 10 to the 9 solar masses by redshift 6. Even in this optimistic scenario that doesn't take into account disruptive events, we are a bit tight in times, so it would be advantageous to have bigger seats, and I'm going to do this with a brief episode of super Eddington accretion. The model that I'm going to present, if you want to put in a context, is in the scenario, is in this scenario, which is direct collapse of gas in a protogalactic halo. These are different channels that have been proposed to form massive black holes. For instance, another popular one, more recently proposed, is the merger of pop-free star remnants. And actually, both these mechanisms have the common problem how to dispose of the angular momentum for the matter to reach the center, and maybe the need of super Eddington accretion. Okay, so how actually you form by direct collapse of gas a black hole in the center, it is a debated issue, and actually it's very interesting. It will be part of my future research, but I'm not going to touch it. I just want to tell you that some problems that involved in it. So first of all, you have to dissipate the angular momentum of the gas, and this take into account possible fragmentation. So you have to study the stability of the gas prior to the formation of the central object. So that's then, even if you manage to bring matter toward the center, then is this direct collapse going to form a star or a black hole? So is nuclear reaction important? And this actually is a very interesting problem. And in the end, when you have solved all this problem, you can say, okay, what is the seed mass that I'm going to create, and that is enough then to build up 10 to the 9 solar masses by redshift 6. Okay, so I don't address all this, as I said, but I start assuming that in my protogalactic disk, so in this cartoon, let's say that these are the innermost 10 to the 16 centimeter. Okay. This is the proto-galactic disk. I put a seed black hole, like, I don't know, 10 solar masses. It doesn't really matter the initial mass. So it switches on, and the feedback luminosity inflates the innermost part of the disk that are optically thick. Okay, and so what you form is a torus that is pressure supported and not rotationally supported. Okay, so we call. Oh, did I say that? No, I didn't say. All I'm talking about is a paper that I made in collaboration with Mitch Bigelman and Philip Armitage. So I forgot to make the reference. So we call this configuration, so a black hole embedded in a massive gaseous envelope, a quasi-star, because in fact has a lot of similarities with a star, but the luminosity comes from accretion and not for nuclear reactions. So you can take this object and study its structure. So the rest, so the second part of the talk will be my attempt to study the study of the structures of these objects. So I want to find the equilibrium states. So for which set of parameters, so mass of the star, of the envelope, mass of the black hole, and photospheric temperature, for which combination of these three parameters this object can exist. Okay. And in particular, I want to ask to myself, so what is the accretion rate that the black hole in the center sees? So this will be the first. Once I have done this, the other important question is that, okay, can this object exist for any combination of these three parameters? Or at a certain point, at a certain moment, the black hole will be so big that the envelope cannot stick around any longer and is evaporated by radiation pressure. Okay, once I solved, I addressed once I have addressed these two questions, then I can model the evolution of this object, how the black holes accretes, how big it can become, and this will be the last part. I said pressure supported, but will be radiation pressure supported. It will be mainly radiation pressure supported. It's a big star, so we. You mean like pulsations? So in this picture, it has. So what we think is that it's stabilized by rotation, which is something that people invoke as stabilizer for pulsations, because you cannot become catastrophic because you have the centrifugal force. What kind of masses are you talking about the star? Yeah, I will go into this, but basically I find at equilibrium the mass of the envelope is 100 times the mass of the black hole, typically, or 1,000, depends on the. Okay. But yeah, okay. So what's inside? Okay. So, but now I'm going to talk about the source of energy of the star. So what's inside what I call the Bondi radius around the black hole, which is actually my inner boundary condition for the envelope. Okay, so what we have inside is an accretion flow that at the beginning is symmetrical and then become asymmetrical towards the black hole. This is highly optical. It's very optically thick. Radiation is trapped. And then and it's been proved that it develops an entropy gradient, so that is unstable for convection. And in fact, these are convective cells. And so what's happened is that the luminosity that is injected here is transported by convection up to the envelope. And
what are the surface densities or optic depths?
I don't have on the top of my mind. I don't model the accretion rate inside. Yeah, but it should be, I mean, it's, it should be like more than 10 to the 4 tau. Otherwise, you are not unstable. And so since this disk is unstable for convection, you can derive, I mean, very, very easily, that it cannot accrete at the Bondi radius. So this accretion flows has a little bit of angular momentum. So I'm not talking about pure Bondi accretions, because I want a little bit of luminosity. Otherwise, the stars cannot exist. And basically, you have that it cannot accrete at the Bondi rate, but at a somewhat lower level given by this, because convection can sustain only a limited amount of flux. No?
Does that power to assume the CDAP solution, the CDAP slope?
It's you can see it. Do we have it? You can see it. It's that like assuming that the luminosity. You can see in this way. You can see that the luminosity, which is conserved at the Bondi radius, is 4 pi r Bondi. And then the flux, the maximum flux that convection can transport, which is like pressure at the Bondi radius times the speed, right? Because the eddies cannot be supersonic. This is the meaning. You can just transport a flux. At maximum can be sonic, the eddy, okay? So then this is equal, of course, the energy liberated at the innermost stable orbit. Okay, so if you substitute, if you put the Bondi radius, you express this in terms of the Bondi accretion, you get this expression.
But the energy speed in the Bondi is contingently less than.
The energy, sorry?
That when you said C sub C, you could have had a smaller value.
Yeah, in fact, this is the maximum. And in fact, I put an alpha here that takes into account if convection is not that efficient. Okay. I feel like a bride with the veil. So one can estimate this, and so this can be converted in the luminosity that I inject at the Bondi radius, and so which is this plus I said a factor of alpha, which basically alpha accounts for any links, any sink of energy that can be like convection not efficient or jets or wind. These disks, which are convection dominated disks, are very prone to winds, outflows, and so on. And in fact, my parameter in my problem will be alpha times the black hole mass square. In fact, for the lower is the efficiency, also epsilon. The lower, less energy I put in the envelope, the same configuration has a smaller black hole mass. It's stable as a smaller black hole mass. But this, I can come back to this. So, okay, so as I said, I inject this luminosity here, and both the Bondi radius and this luminosity depends on the condition, innermost condition of the star. So I have to solve self-consistently the structure of the star and the accretion luminosity. If I change the star mass, for instance, I change the accretion rate onto the black hole. Okay, so I have self-consistently consider the two. So how I model the envelope above this Bondi radius. So it's, I ask because I want hydrostatic equilibrium equations. I'm looking for that. And allow the pressure to be gas and radiation. Okay, of course I conserve mass, and the energy equations. So I allow the energy to be transported both by convection or by radiation, radiative transport. Of course, conduction is not important here, it's not a degenerate plasma. And so the relative amount of energy transported by convection and radiative flux fix the temperature gradient, so the behavior of temperature. So to check whether a layer in my star is convectively stable or not, so it's stable for convection or not, I use the Schwarzschild criterion, and so so here implicitly I'm neglecting composition variation in the stars, but this is good because we are hot enough that basically we are ionized all the way up to the atmosphere. In the atmosphere we have at most like a few percent of neutral hydrogen, so it's fine. So at each layer I check whether it's stable or not for convection, and like basically if it's unstable, means that the energy that convection is efficient. I assign the adiabatic gradient, which is the gradient, which is the variation of temperature that a convective eddy has as it rises adiabatically through the surrounding layers. So adiabatically without leakage of photons, of energies. And if the layer is stable for convection, I will assign the radiative gradient, which is the gradient of temperature that you should have if you want to transport all the energy by radiative flux. Okay, and then between the convective and the radiative layer, I will interpolate smoothly. So this prescription is correct in the limiting behavior, like in the innermost part of the star, where it's extremely opaque. Convection is very efficient, and the gradient is adiabatic. Close to the photosphere, we are less opaque. Convection is not efficient. Energy transported by radiation, and this is the temperature gradient that you must have. Okay, so in the middle, one should maybe be precise and use the mixing length theory. But I check that qualitatively and quantitatively, my results does not change according how I match the two gradients in the middle. So this how I.
So you said that you have rotation stabilizing.
Yeah, no, okay. So in fact, it was a misleading answer. So when I model, I neglect rotation. Okay, so. And for two reasons. One is pressure supported, so the centrifugal force is small. And but there is another thing that is not that's less clear, that is a good approximation, which is differential rotation within the envelope, like we see in the sun, that we do have differential rotation as a function of latitude, actually. Okay, but nobody we observe, we have extremely good data, but modeling is not that easy. So here I'm assuming that is rotated solid body, basically. Sorry?
It's only good for inner convective.
Yeah, no, I know. No. I'm saying that this is something that it's less clear, that is good approximation. And but even in the sun, in the convective part, we see differential rotation as a function of latitude. So so when I talked about stability, I mean we know that big stars have these problems, and when is the radiation supported, the total energy is zero, and so it's very easy to unbound, right? But if you do like a little bit of stability and put and assume a little bit of rotation, then it's stable. Okay. Is that okay? No. Okay, here just okay. Since I'm modeling a star, a quasi-star, which is born in pristine gas, what I use are opacity that are metal-free, and in particular, I want you to notice that the opacities are decreasing with temperature and decreasing with density. And in the region that is close to the photosphere, the main opacity is given by bound free absorption onto hydrogen. Okay.
So what are the kind of luminosities you're talking about, and what's the radius of the star?
Yeah. Okay. Okay, I can anticipate just the last, but this is just to say that I checked a posteriori that my thermal and mechanical equilibrium assumption are correct, and then now the results. So what I find in the structure is that you have an innermost part of the envelope. As I said, so the mass of the star, of the envelope is usually, we will see a diagram, is usually a factor of 100 more massive than the black hole. You need so much mass to absorb the energy that the black hole is emitted. And you have that this innermost part would contain, at the end of this life, of the life of the quasi-star, contains 98% of the mass. So most of the mass is in this convective region. Then you have an upper part, here an upper layer, which is very thin, can be at the end of the life of this star is 10%, and is radiative. I didn't say that here you have, I don't know if you are familiar with, but you can just actually fit it with a polytrope with index n equals 3, and you have constant temperature and density, while the temperature and density here decreases generally, but close to the end of the life of this star, it does funny things. But I don't know if I can have time to go there.
Presumably you've got constant entropy.
Yeah, also. So,
N equals 3 molecule is pretty highly essentially concentrated even without alcohol. So you might imagine that even a small black hole would cause a significant central peak in
I mean, you are talking about in the black hole, in this region. Yes, if
the
the
question is how I mean, obviously it doesn't affect things very much outside of the bond.
so as yeah. So I'm talking about this part outside the Bondi radius. Okay. So inside, of course, there is the presence of the black hole changing this profile. Okay. But here, actually, okay, if we didn't have an accretion disk, of course you have a peak in temperature and density, of course, because you have a mass concentrated in the center. But then you have an accretion disk with its own properties, so the density of profile, the profile of temperature and density are different inside. And here what you get, because it's a convective, do you want to know why it's constant? No. Okay. I know. So.
Do you show a plot of the entropy, or have you plotted up the entropy?
So basically the entropy it's constant, right? Because
It ought to be,
yeah,
if you're convective
yeah,
infection,
yes, in fact, yes.
Yeah. I'm just wondering if you've actually checked and plotted it and see that.
No, but no, I didn't plot it.
Probably a worthwhile exercise.
Yes, but this, yeah, actually I can check later. Actually, analytically. I can check analytically because if the density and intensity are unconstant, and the entropy is log.
The pressure's from the radiation, right?
Yes.
It's just T to the 4.
Yes, in this part, the pressure, actually, yes, the ratio of gas pressure to radiation pressure in this part is fixed by the mass. This is like, And this, so since we are talking about big stars, is all like a radiation gas pressure is only a few percent or less in this part. Okay.
So it's all radiation pressure.
Yes. Yeah. And while here you have that this ratio increases a little bit for stability, actually. And then I find that whatever are the combination of masses and the photospheric temperature, these stars are 100 EU, more or less. So really big stars.
And the luminosity?
So the luminosity will be 10 to the 42, 10 to the 42, 10 to the 43 erg per second. And we are coming to that, to the luminosity part. So, okay, so the first result, which is the most important, is that if you check at the equilibrium state, which is the luminosity at the photosphere, you find that the accretion rate onto the black hole adjusts so that the energy that is emitted by the black hole equal the Eddington limit for the total mass of the quasi-star, mass of the envelope plus mass of the star. So basically, so the black hole sees super Eddington accretion. Okay, so which is, I don't know, the trick here is that the energy, you can have a highly super Eddington luminosity transported by convection. Okay, so you can sustain a higher luminosity, and then when you release it a large enough radius, actually, in large enough radius where you have that in it you have most of the mass, you release this energy by radiation, but you have enough mass to keep the star in place. Okay. So that's why we can be super Eddington. So the black hole, which is inside, because it has this huge envelope mass, it is super Eddington accretion.
So this would be then affected if you allowed for super Eddington flux through the outer envelope, if you had an homogeneous outer envelope as well.
If you have
had super Eddington radiative layer with inhomogeneities in it,
yes.
that would affect the model as well.
Yeah, you mean in the radiative layer with photon bubbles? Yeah, but here you can arrive to that part. But the nice things about having a lot of mass around is that this Eddington limit can be here 100 times larger than you can get with simply a dishomogeneous atmosphere. Okay. So then the third result. Okay, so I answer my first question, which is the accretion rate that the black hole sees in this configuration. Okay, so the second my second question was, okay, does this configuration exist everywhere in, for instance, temperature, photospheric temperature, black hole mass space? The answer is no. Okay, the answer is that you have, for each black hole mass, you can have all this photospheric temperature, but you cannot be cooler than that. Okay. So you have a forbidden zone below which I don't find hydrostatic solutions. No hydrostatic solution exists. Okay, I'm going to explain this. It's like just analogous to the Hayashi track that probably you are familiar with. That for protostars or like red giants have evolutionary track which are parallel here, because there is this forbidden region. They cannot be cooler than that. There is no solution for a fully convective stars in hydrostatic equilibrium here. And the same happened here because we have that our opacity is very sensitive to temperature, as it happens with H minus here. In fact, okay, so this is opacity in the radiative zone, so in the most outer part of my star. and I plot as a function of temperature. Okay, but this is the photosphere. And these are 4 models for the same black hole mass, but I'm decreasing the photospheric temperature, cooler and cooler, which also means that the envelope mass is smaller and smaller. Okay, and so you have, if you see the opacity here at the photosphere, as the temperature goes down, the photospheric opacity drops. I mean, I changed the scale here, so it,
The same, just different scales. The same plot, just on different scale.
yes, I had to change the scale because we are 10 to the minus 4 now, but it's the same plot for 4 different temperature. Okay, so this just to tell you how sensitive is the opacity at the photosphere. So as it becomes cool, it becomes less and less opaque.
It's just the electrons recombining out with protons. Right now it's hydrogens becoming neutral.
It's becoming neutrals.
You were showing basically
Yeah,
electrons.
yes. Okay, so this is its this is its electron scattering, and this is the bound-free opacity. This is its bound-free. Okay, so this is bound-free, and this is bound-free, and this is its the electron scattering. Okay, so what's happened? So as the temperature goes down, I'm reaching a dangerous zone. And I said that there is a temperature below which these stars cannot exist. I don't have hydrostatic equilibrium. And this is why I try to explain by words. So as I said, as I decrease the temperature, the opacity drops. And so the photosphere sinks in, right? So if the temperature is greater than this mean temperature, the pressure at the photosphere can adjust to a higher value of pressure, so that it reaches again hydrostatic equilibrium. So it drops in, but the pressure rises, so I find an hydrostatic equilibrium solution. When I go below this temperature, means that I'm very close to the convective zone, where all the pressure is basically radiative pressure. So I cannot sink in and increase my pressure, because the pressure is depends on temperature only, basically. So what's happened is that when I'm below this temperature, the stars contracts, but the pressure is not enough for to balance the gravitational pull. So it contracts and heat up in a dynamical timescale, and it comes back to a solution where T equal T mean. Okay, so it's a forbidden zone. Every time I go down there, what's happened is that in a dynamical timescale, I come back to the solution T equal T mean. Okay. So I think I don't have time to tell you how I estimate T mean. I can do later if you want, because I want to go to this part. So, okay, so we know that the black hole sees super Eddington accretion. So I know that the black hole, as a function of time, accretes like this, where this is the Eddington limit for the whole star. Then I can, but the envelope too is accreting from the disk, and this is a parameter. I don't know, 0.1 solar mass per year, for instance. So at each step, I make the star accreting and the black hole accreting. So the envelope and the black hole are increasing their mass. And I can do this because the dynamical and thermal timescale are very short. So every time I change one mass, this adjusts immediately. Okay, so I can model evolution as a subsection of equilibrium states. And so this is its mass of the envelope in solar masses, and this is black hole. And this is, again, the forbidden zone. So I can make them evolve. So as the mass increases, the envelope mass increases, the black hole mass increases, and I'm going towards this direction. What the temperature at the photosphere does. In fact, we find this relation, and we find that the temperature decreases. So as the quasi-star and the black hole becomes bigger and bigger, the photospheric temperature decreases. So let's take this, decreases. until it hits the limiting temperature below which it cannot exist. Basically, at this point, the black hole managed to unbound the envelope. Okay, so evaporates the envelope. And what you have is that you remain with the protogalactic disk and the black hole in the middle. And this black hole is like an intermediate mass black hole. Depending on the efficiency alpha I was talking about, can be like 10 to the 4, 10 to the 3 solar masses. And then normal accretion will start.
What's the time scale?
So basically, there's evolution like this in a few million years. So at z equal 6, it's z equal 10, it's like nothing. So now we have an intermediate mass black hole, a redshift 10 or so. And so we can ease the requirement of continuous super Eddington accretion in order to have supermassive black holes at redshift 10.
You said it evaporates the entire envelope. Why doesn't the mass just fall below the equator?
So what did you say?
You said it suddenly gets rid of the entire envelope?
Yeah, the radiative pressure, the radiative force wins over the gravitational pull, and you
Once the mass
evaporate.
falls below the critical value, the temperature will rise above 10 to the 4.
Yet, so basically, what happens? What think would happen? That this is the black hole has become it keeps accreting, and in the end, you cannot sustain this envelope anymore around. So that's what we think it happens. That the radiation force or the luminosity prevents this envelope to be there below this point. There is no equilibrium anymore.
If you get rid of a little bit of mass, there will be
There will be accretion in the plane, but not around. Do I answer? Just to finish, just a curiosity. It's if you want to observe these things in the sky, if you would be able to observe. So the accretion rate gets longer as the black hole increases. So these things the quasi-star spend most of their time close to the minimum temperature, like red giants spend most of the time close to the Hayashi track. And so if you want to see where in the H luminosity temperature diagram they are up there. So what you see, this is the critical temperature. These are red giants. And this is like 10 to the 43 ergs per second, 10 to the 10 solar luminosity.
So you've essentially been describing a Thorne-Zitkoff object.
Yeah, there are similitudes. Yeah, so.
Did you compare? Did you get similar results?
Yes, so the Thorne-Zitkoff object has a neutron star in the middle, and they have envelope comparable to in mass to the central object, and so they have and they don't treat the radiative layer external, I think, and that. And they have they have also what they have actually is that from the envelope to in the way to the neutron star, they have nuclear reactions. I think this is because the neutron star have a surface, so the density it's higher than what we get. I check a posteriori that the rate of nuclear reaction in our case is very low. We are not.
What are the temperatures you're considering?
Yeah, so are never higher than a few million Kelvin.
You mean temperatures at the bonding radius?
Yes, yeah. Then it decreases.
But of course they're higher than that.
We check that you never get very hot, so hot that nuclear reaction can be important even in the disk. Yes, and that's it. So the conclusion I already said. So.
What do you mean when you say it's never important inside the disk? Is it not important in the sense that
Not the rate of nuclear reaction is lower than the luminosity given by accretion. It's higher than the luminosity given by nuclear reaction, so you can ignore.
That's not the same thing as saying that the metal production is important.
The metal production?
No, you use a 1060. At this low temperature, how would you use metals?
Well,
Yeah.
it's-
You
it's
have hard
short
time
side-
with the
it's
PP.
short side, the body radius is convective, so if we bring it better on one side, you can get that material out.
Yeah, that's true. But yeah, no, that's definitely true.
Affect the capacity of certain or something like that.
It depends how, I mean, at this temperature, like a few million years, like you are very efficiently producing metal. But it's true that, I mean, you might have a pollution of metals into the envelope by convection. I didn't check this, but like you cannot really have more than a few million degrees even inside. So already you have problem with the PP process. So
So how much is disturbance release? It's like 100 or 1,000?
how massive is
A black hole when it's
like a few 10 to the in this, for instance, in this example is a few 10 to the 3 solar masses, or here it's close to 10 to the 4 solar masses. Yeah.
I'm still wondering about the instability.
Yeah.
Position instability.
Yeah.
When you say location stabilized, is
Mhm.
that a statement?
It's a speculation of mine. Okay. I mean, in general, people invoke rotation to stabilize. Like big stars are radiation supported, right? Are radiation pressure supported, and they have.
It's a very massive star for exactly that reason. It's
So,
A bunch of reasons
sure, but
What
you
is-
don't see like 300 solar mass stars because presumably they are radiating to the position they are stable.
yeah, they are. So definitely, if they are not rotating, they are a pulsation unstable.
Why would rotation do anything to stabilize? It's not clear to me.
So basically, the oscillate. You are asking me why radiation is. So radial pulsation, if you have an extra force, basically you quench the pulsation so that they never become very strong. Okay, so that's.
Unless you're adding random barrier, you're not rotating that anywhere close to break up, right?
No. Actually, I'm very slowly rotating, but.
Right, so it's not going to break up. I would
Well, I think the upshot is she's calculating an equilibrium and she's not sure that it's stable.
exactly, that's
That's
right.
fine.
Well, but if it's unstable, then you also have to use it.
That's true. But you have to do more calculations to see if it will. She's worried about you losing your whole envelope and, sloughing off.
No. I mean, we are aware of this. Actually, Thorne, Zitkov have done stability analysis, and they find the same. I mean, everybody's when build up this big object. I don't know, Hoyle and Fowler, also. I mean, but then it's such a complicated problem. The stability one is that they would need the pulsation. I mean, I went through the literature for these big stars and so on, and I would need the other 8 papers to tell you whether they're stable or not. So I invoke rotation because people usually says, okay, this is efficient, but I cannot guarantee because I didn't. It's a very complicated issue. I can refer to the literature if you want.
Is that the same thing they invoke when they're trying to make these 500 solar mass top 3 stars? I mean, is that the argument that he's there? Because I know they make like these, the guys making these top 3 stars, they have some model where they think it's stable, I guess, 500 solar mass top 3 stars.
Mhm.
The same sort of, you have the same sort of problem there. Yeah, I don't know. I don't know.
Yeah, they must have, but I don't know.
Yeah, they haven't done the radiation transfer exact, so just say. Yeah, they have a huge sinkhole. Yeah, they don't
So there's no reason why Elena has to answer the question. Are there other questions?
So, I mean, does cosmology constrain the rate of production of these? I mean, how,
The cosmology constraint.
like, how many of these should be
Yeah.
produced?
So of course, yeah, that's a good question. So we have to put this is a physical mechanism, like the job I've done. But of course, you have to put this in a cosmological context and say, okay, in how many halos you can have such a configurations, no? So for instance, not all halos you can have a collapse at the center because you have to have a small enough spin to have a small enough angular momentum to go. So to collect the mass and have this object. And then you have to let these halos evolve. Okay, so I think that preliminary calculation. I know that preliminary calculations have been done by Marta Volonteri et al. But they are preparing another more specific paper using this mechanism, and to check whether you can see observations. Yeah. Okay.
Okay, let's
Thank you.